Okay, let's get started. So I think we have fewer students here. I think because we are in the exam period, so I think students studying some other classes, other courses. Okay. Okay. So in the previous class, we learned about some basic conventions of system design. So actually in chapter 4, as I mentioned, so we will learn about how to design hardware architecture of processor. Okay, so which means that actually in chapter 2 we learned about the instruction, which is rather a software part, right? Because even though we use the high-level programming languages, these language codes are translated into instructions. The instructions are still software part because it's not hard. So it's not real hardware. Okay? Instructions are software, but in order to execute instructions, we require hardware components. And then actually, we need a real CPU or real processors to execute instructions. So which means that we need to build computer systems using real hardware. So in chapter 4, we will learn about the hardware architecture of basic processors. Okay. So is real hardware. So I mentioned that the processor is kind of a data system, and then data systems handle only 1 and 0. So which is the binary data, okay? And then 0 is the low voltage, and then 1 is the high voltage. Actually, the processors handle the electric signals. And then we also learned about the basic components of the data systems, and then we learned about the combinational element like this AND gate or adder. So I explained that the combinational element, the output results are determined by only input values. So which means that the input values are changed and output values are also changed after some delay. Okay, because we live in real world, which includes the time component. And then what is the sequential element? So the output of the sequential elements are decided by input signals and states stored in this element. Okay, the output result of the sequential elements are determined by input signals and states. So that is the kind of memory part. Okay, so when I mentioned the sequential element, we learned about the deep flip-flop design because we frequently use these deep flip-flops. And then actually in order to implement the pipelining, so we also require these deep flip-flops. Okay, so also I also mentioned covered some basic design with the system value. Okay, I hope you can understand this example. Okay, so in this time, so I will explain how to build single cycle processor. So what is the single cycle? So single cycle means that the single cycle. So when I mention the processor is this design, this system. So which means that computer processors work with clock signals. Okay, so single cycle means that this processor executes a single instruction per clock cycle, which means that within one clock, this processor complete executing of a single instruction. That is the definition of a single cycle processor. So So now I will explain which steps are required for executing instructions. Okay. Okay. Let's see the example of add x1, x2, and x3. So let us assume that we try to execute this instruction add x1, x2, x3 with a single cycle processor. And then, then where is this instruction? So what does that mean? I asked where is this instruction? Right. So instructions are also kind of data, and then all data are stored in memory. Okay. So in order to execute this instruction, then a processor needs to read this instruction from memory. Okay. Then what is required? In order to read some data from memory, then we require address, right? And then I mentioned that the address of instruction is program counter, right? So the required step for reading instruction from memory is so firstly we need to set PC, the program counter, and then with this program counter, a processor access the memory that includes the target instruction. So it means that this is the memory, and then this target instruction is stored in some entry in the memory, and then with the target PC, then processor access this memory, and then read the instruction from the memory. Okay, so this step is called the instruction fetch. Okay, so it's instruction fetch. Okay, so now a processor fetches the target instruction from the memory with the program counter. And this instruction is the binary data. Okay, like the 10001111 blah blah blah, something like that. So actually, when our data is read from the memory, then this data is the binary data. So if we just see this binary data, then we don't know what is the meaning. So which means that what is the definition of this data? So we don't know. So we require actually a processor requires to decode. So decode means that it is the encoded data, which means that our specified instructions are encoded into binary data. So I explained this encoding in the chapter 2. Actually, memory includes the encoded data. So in order to understand which instructions are included in this data, then a processor needs to decode an instruction. So we require decoding. So and then this step is called the instruction decode. Okay. So instruction decoding instead. So we also learned that how to each field of the instruction data are organized by a certain instruction. So by checking each field of the instruction data, a processor decode this instruction. So for example, so this is the add instruction, add x1, x2, x3, and then this is the R type instruction. And then we learned that this instruction has the OP code field, and then RD field, and then function 3, or RS1, RS2, or function 7 field, right? So by checking the bit data in each field, then a processor decodes the instruction. So which means that from the binary data, like the 111100, blah, 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 then this data is decoded into the add x1, x2, x3, okay? So then processor can understand which instructions are fetched, okay? And then if we see that this instruction add x1, x2, x3, then we can know that this instruction requires operand from register file. So which means that a processor needs to require the operand data from register file, and then the location of the registers are specified by register number x2, x3. So instruction decoding step also includes the read operand data from register file. So instructions are decoded and then when an instruction is decoded, and then a processor can know which register data is required. Okay. Then with the decoded register number like 2 and 3, then a processor reads data from the register file. And then this process is also included in instruction decoding step. Okay, that is the second step of the instruction execution. Okay, then if we see that this add instruction, not to execute this add instruction, then we require operand of the add instruction. And then in the instruction decoding step, a processor already they require the data from the register file. So which means that the operands are ready. Then which step is it required? So operands are ready. Then we need compute. A processor needs to generate result of add instruction, right? So operands are ready, and then a processor needs to execute actually add operation. So this is the hardware. So which means that in order to perform add operation, then a processor needs to have adder. Okay, adder hardware. So we learned about the adder in chapter 3. That's why we learned this hardware component in chapter 3. And then this step is called the execution. So execution means that, so if we see this instruction, then this target instruction requires some specific operations. So add instruction requires the add operation. And then using the operand of the add instruction, then a processor performs the add. Okay, which means that two operands are provided to adder hardware. Then this adder will generate the result of the x2 plus x3. So this is the result. Okay, this is the execution step. But we can think of another different type of instruction. So this different type is the load instruction, like load x1, x2, and offset. So the target of the load instruction is different. So which means that actually archive instruction, arithmetic or logical archive instructions require arithmetic hardware component, but load instruction is different. Load instruction requires the memory, because with the address, with the computed address, and load instruction accesses memory. Okay, and then for some memory type instructions, such as the load or store instructions, need to access memory. So this step is called the memory step. And then actually, memory type instruction performs is only memory step. Okay, only memory type instructions requires the memory step. But our processor needs to execute the all type of instructions. So which means that processor needs to also include the memory step. Okay, in the memory step, then using the calculated address, the memory is accessed. Okay, so memory. Then when the memory is accessed, then we can also store the data to the memory. And if the load instruction is executed, then data is read from memory. Okay, so this becomes the result of load instruction. Okay, so in the execution step, the result of R-type instructions, like the arithmetic or logical instructions, are generated. And then in the memory step, the result of load instruction is generated. Okay. And then the final step, so what is required? The results are generated. And then if we see the instruction of the RISC-V ILA, then we can find the destination register. So we can, in the R-type instruction, we can find the destination register, okay, RD. So results are calculated, and then results are read from the memory. And then this result need to be stored in the register file, right? This step is also required. So with the generated result are written to the register file. So this step is called the write back. Okay, but because the registers are already accessed by instruction during the instruction decoding step, and then the result is written to the register file. That's why we call this step as the write back step. Okay, so in the write back step, the results are written back to the register file. Okay, so these are 5 steps for executing instructions. So which means that in order to execute the instruction in the computer hardware, like processor, then a processor needs to perform these 5 steps. Okay, and then based on the required steps, we will design the processor hardware. Okay. So in this class, we will first cover how to build data path of the processor design. So data path means that data path includes the hardware element, the hardware component. So actually in the previous class, we learned about the several hardware components, such as the adder, multiplexer. Also, there are several other hardware components, such as the register file and ALU. ALU is some collection of arithmetic unit. Okay, so data path includes the hardware element, and the data path also includes the connections between hardware components. So what does it mean? So in the previous slide, we learned about the 5 steps. 5 steps for executing instructions. So which means that firstly, we need to read instruction from the memory. Then the result of this step is the instruction. And then in the instruction decoding stage, then a processor decodes the read instruction. So which means that the input of this instruction decoding step, it becomes the instruction, which is the output of instruction fetch step. So in order to perform multiple operations required for executing instructions, multiple hardware components are connected, and then the output of a certain component becomes the input of next component. So for example, so instruction, so this is the instruction. So instruction on instruction can be read from the memory. Okay, then instruction is the output of the memory. But in order to decode this instruction, a processor needs to analyze the instruction, which means that a processor requires the decoder. Decoder is also a hardware component. So instruction becomes the input of the decoder. So in order to deliver some data to the hardware component, then we need to connect the output of the memory to the input of decoder. So data path also includes the connections between hardware components. So firstly, we will learn how to build data path of the processor, and then we will learn how to control these data path elements. Okay. So these are examples of data path elements. So register file, and then ALU, and then also multiplexers or memories. Okay. And then I will explain the data path of the single cycle processor step by step. So instruction fetch. So as I explained, the instruction fetch, in the instruction fetch step, a processor reads a target instruction from memory. Okay, and then let us assume that instructions are stored in the instruction memory. Okay, so this is the instruction memory. So actually, the instructions are firstly stored in the main memory, but just forget about the main memory. So then we assume that the instructions are stored in the instruction memory. Okay, so the instruction memory. Then what is the read purpose? What is the required operation? So as I mentioned, so we need to get program counter value, and then here is the program counter value. The program counter value is stored in the program counter register. Okay, so in chapter 2, we learned about the general purpose register and program counter register. The program counter includes the program counter value, and then using this program counter, then as you can see, this is the output of a program counter. Output of a program counter is connected to the address port of instruction memory. So which means that the program counter is provided to the address port of the memory, instruction memory. Then what will happen? So this is the data path element, and the address is given. This is the input. Input is the address. Then what is the output? Output is the target instruction. And then the entry of this instruction is pointed by address. So when a program counter is provided to the instruction memory, then a processor can read instruction. And then we know the size of the instruction is the 32-bit, it's a 4 byte, then it's the 31 down to 0. So this is the data path element, data path for instruction fetch step. Okay. And what is this? So if you see that this path, then you can find, oh, this is the PC, So this is the program counter, which is used for fetching instruction, and then this instruction is the current instruction. Then if you see that this path, then you can find the PC is here. Then this is the adder, okay? It's the adder. And then as you can see, the another input of adder is the 4. Then what is the output of this adder? This is the PC plus 4. And then PC plus 4 is given to the program counter register. So what does that mean? So actually, this program counter is sampled by clock signal. And then program counter is the E flip-flop. So we learned that the input of the flip-flop is updated to the output of the flip-flop at the rising edge of the clock. So in this figure, it's the PC, and then this is the PC plus 4. Then PC plus 4 is connected to the input of the program counter register. So, and then this PC plus 4 is updated to the PC when at the rising edge of the clock. So it looks like this. So this is the clock signal. And then this is the rising edge. So this is the current PC, okay? The current PC. And then within this clock period, PC plus 4 is calculated by this adder. Then in the next clock, it becomes the PC plus 4, right? You understand? So the current clock period, the PC, and then the PC plus 4 is calculated. And then this PC plus 4 is updated to the program counter register after the rising edge of the clock. Then PC becomes the PC plus 4. So what does that mean? So in chapter 2, so we learned if there is no branch instruction, then the program counter of the next instruction is the program counter of current instruction plus 4, right? Because the size of the normal RISC-V instruction is 32, the 4 bytes. Okay, so that's why the PC plus 4 is calculated, and then for the next clock, the PC becomes the PC plus 4. Then the next instruction is read from the instruction memory. Okay. So this is the instruction fetch step of a processor. So what is the output? Output is on instruction, so which is the current instruction. Okay. Then how can we write the behavioral model of this instruction fetch stage? Okay. So this is the PC register. Okay. So this, and then as you can see, you can find the snippet of the system Verilog code. And then PC register is the 32-bit register. Okay. And then actually the PC is the address. So then this, so which means that, and then we are learning about the 32-bit computer system, so which means that the address bit is the 32-bit. Okay, so PC is that's why the PC is the 32-bit register. So as you can see, you can find the current PC, the PC underbar current, and then size of the PC is the 32-bit. Okay, now how the PC is updated? So I mentioned that the program counter register is actually E flip-flop. So this code is very similar to the basic flip-flop code, right? So this is the sensitivity raised, and then you can find that the positive clock, and then the asynchronous negative reset. So if the reset becomes the 0, then PC becomes 0. Otherwise, then PC is incremented by 4. Like PC on the back curve plus 4. Okay. So actually this part can be implemented like this. Okay? It's a behavioral model. And then as you can see, this behavioral model explains what I explained for the program counter. Okay. And then instruction memory. So what is the memory? So this is the definition of memory. A memory is a data array. So you can store many data elements inside of memory. Okay. And then memory means that a data array indexed by address. What does that mean? It looks like this. So there are many entries. And then we can access a certain entry with the index. For example, the first entry, the index of the first entry is the 0, and then the second is 1, 2, blah, blah, blah. Okay, then in order to access this entry, then we can access the target entry with the like data indexed by 2, and then this is the address, right? So this is the behavioral model of the instruction memory. Okay, so you can find that which means this memory has the 256 data element, and then the size of a single data element is the 32 bit. So it is because the size of a single instruction is 32 bit, and then the number of entries is 256. So how can we access the target entry? So it's simple. So this is the array. So we can find that the data and index. And what is the index? What is the index for this data? It's address. What is the address for memory? Instruction memory. What is the address for instruction memory? Right, current PC. It's the PC underbar current. Okay. So using the program counter and using the program counter as the index of the data array, then we can access the instruction memory. Okay. And let's see the decoding step, instruction decoding step. So, so this is the instruction fetch step, and then in our computer architecture, we frequently use the abbreviated form for the some step. So, instruction fetch step is I frequently use the IF for the instruction fetch step. Okay, and then let's see the decoding step. So this decoding step is called the instruction decoding. So which means that it's called the ID step. So it means the instruction decoding.
전 페이지
예.
데이터 어레이에 들어가는 PC 파란색을 바로 나눠줘야 돼.
Right. Yeah, very good. Yeah, right. So he asked that we need to divide the program counter by 4. So it is because this is the 4-byte array. So which means that the PC curve need to be divided by 4, right? Because the address is the byte address. Yeah, it's a good point. Okay, PC. And how can you use the PC curve divided by 4? Right. We can use the PC curve 31 down to 2. If we just eliminate the LSB 4 bit, LSB 2 bit of the program counter, it is equivalent to the PC current divided by 4, right? That's a good point, right? Okay, so let's see the instruction decoding step of the processor. So for the R5 instruction, actually, I mentioned that in the instruction decoding step, the instructions are decoded, so which means that the processor analyzes the fetched instruction. So instruction is the 32-bit data, and then also we learn how the instruction is encoded, and then which means that this 32-bit data has multiple fields like the OP code, RD, and then function 3, RS1, RS2, and then function 7 field. So simply we can read some register numbers from the instruction like here. So this is the 32-bit instruction data, like inst 31 to 0. And in order to analyze this instruction, which means that in order to decode the instruction, then we need to we can split the instruction data into multiple fields. Actually, this instruction encoding rule is defined in instruction set architecture. Then we can build the instruction decoder based on the definitions in ISA. Okay, so we can use the first inst 6 down 0 for decoding OP code. Okay, and then if we read the inst 7 and then 11 down to 7 from the instruction data, the 11 down to 7, then we can know the destination register number, right? Just simple, right? And then if we read the 14 down to 12, then this is the function 3 field. And for the RS1, it's the 15 to 19, right? So it means if a processor reads the instruction data, pin number 19 down to 15, then we can use this data as the RS1. Understand? It's the same. The RS2, if we read it's 20, it's 24, right? So if we read the instruction 24 down to 20, then a processor can get RS2. That is the source register number 2. Well, it's a simple. You can just split the read instruction into multiple fields. And then if we split this instruction into multiple fields, then we can get the RD, RS1, and RS2. So we can get the OP code and then function 3 and then function 7 field. And then based on the OP code and then function 3 and then function 7 field, a processor can know, oh, current instruction is add instruction. Right? Or the a processor can know a current instruction is a specific instruction. Okay, so like okay. So you can you can find the OP code field and then function 3 and then function 7 field. So if we use the add instruction, so if we the OP code field is the 0110011, and then function 3 is 000, and then function 7 field is the all zeros, then processor can know that current instruction is the add instruction. Okay, and then as I mentioned, if a processor lists each field like the RD, RS1, and RS2, then a processor can know the required register numbers. Okay. Then, using the decoded register numbers during the instruction decoding step, a processor accesses the register file. So if you see that this register file, the register file has 3 register number port, and then 1 write data port, and then 2 read data port. Right. So if we see the add x1, x2, x3, then this R-type instruction has 2 source registers. So which means that this R-type instruction requires to read two operand data from register file, right? RS1 and RS2. So from the instruction, some instruction field is given to the read register number 1, and then some instruction field also given to the read register number 2. And then this register file is also a hardware component, which means that if the read register number is given to the register file, then the processor can read operand data from the register file, right? The RF RS1, the indexed by register, also the read data 2, RF index RS2. So the data can be read from the register file. Okay, so operands are ready. And what is the right register and then write data? So if we see that this instruction, then we can find that this is the RD. And then when in the write back stage, then the results need to be written back to the register file. So which means that with the RD, which is an instruction, this is the RD, is given to the write to register port and then result. So this write data means the result of the add operation. So the result is given to the write data. Okay. And the register file requires the control signal called the read write. Why? Some instruction like add instruction has the RD. Okay, so which means that the result of add instruction is written back to the register file. But like the store instruction does not store result data to the register file. So some instructions do not need to result data to the register file. For example, branch instruction also. Branch instruction just change the program counter, does not change the register file. So some instructions does not need to data to the register file. So we need to distinguish these different cases. Okay, using the control signal. Okay, that's why the register file has the read write port, and then this read write port is the control port. And then as you can, it's easy. If the read write becomes the 1, which means that register write is enabled, but if not the 0, then the register write is not enabled. is disabled. Okay. So this is the register file. And then let's see the behavior model of a register. So, so when we learn about the register file, the general purpose registers of a RISC file, then you can know that the RISC file has the 32 general purpose registers from X0 to X31. And then we can access the target register file using the register number. So which is very similar to the memory component, right? So we can use this register number as the index of the register data, right? So if you see this part, then you can find that. So this is the size of register, a single register file, which is the 32, the width of the register file. And I explained that the RISC file has 32 general purpose registers. So this array, RF underbar data, has the 32 elements from 0 to 31. Okay. It is because the RISC file supports the 32 general purpose registers. So how can we access this RF data? Using the RS1, RS2, and RD. Okay, then you can find the read operation here. So read underbar data 1. So this is the output port of the register file, right? So how can you read the data from the register file? It's also simple, like RF underbar data, and the target data is indexed by, so you can find that this is the 1, RS1, okay? Then we can read the required operand from the register file. And then read data 2 is also the same. So we can read the target array of the target element of the register file using the RS2, right? And then this is the write operation. Actually, not to implement this register file, the register file needs to be with clock signal actually. Okay. So as I mentioned, the read write is the control signal, and then the write operation is enabled only if the read write is 1. Okay. So if you see that this behavioral model, so you can find the read write here. So if the read write becomes 1, this condition becomes true, then what should we do? This part. This is the update. So which means that the target element of a register file is updated. Then how can we know the target of this updated register file? So using the RD, okay? So the target is the RF underbar data and indexed by RD. So this is the target, and its value. It is updated by, I forgot, write data. Okay, this which means that it's the write data. Okay. So I hope you can understand the behavior model of the register file. Okay, that's just a data array, and then data array can be accessed by RS1, RS2, and RD. Also, just remember that register file requires control signal called read write. Okay. And then also, this is not a instruction decoding step, but execution step is rather simple. This is because the actually operand of the execution step is prepared by register file, and then actually we can connect this output of the register file into the input of the ALU. Okay, so ALU means the arithmetic logic unit. So this becomes the ALU. So actually, as I mentioned, the ALU is the collection of arithmetic or logic hardware units. So for example, so in order to execute the add instruction, we require the adder. So in order to execute the exclusive OR, then we require exclusive OR logic. Now it's the same for the and the and if we need the sub, then we need to also require the subtractor. Okay, so for the R type, for the arithmetic or logical instruction, we require various kinds of operations, so like add, sub, exclusive OR, and OR. Okay, and then these hardware units are included in the ALU, and then the required operations are selected by also the control signal called ALU operation. So for example, if the ALU operation is 0000, then add is performed. Okay, using the two inputs of ALU. So for example, so if we execute the add instruction, then we can read the required operand from the register file. So this is the output of the register file. So read data 1 and read data 2. And then in order to perform the x2 plus x3, then these operands are given to the ALU. So we can just connect the read data 1 port to the input port of the ALU, and then read data 2 to the another input port of the ALU. Then ALU performs the add configured by ALU operation, and results are generated. So this is also combinational logic. So what does that mean? If the input is given to the ALU, then ALU will generate the output after some delay. Okay, so ALU result is generated. This is the execution step. So for the execution step, so we need to implement the ALU. Okay. So actually, the ALU is the collection of the hardware, arithmetic or logical hardware units. So you can also implement the ALU using the combinational logic. And then the output of the ALU are selected by ALU control signal. Okay. And then let's see the load store instruction. So if we see the load instruction, like load x1, x2, and immediate. So load instruction is the I type instruction, right? So which operation is required? So first, in order to execute the load instruction, we need to perform the x2 plus immediate. And then it becomes the address of the load instruction. And then using this address, and a processor accesses the memory, and then this memory is the data memory. Okay, so the instruction is fetched from the instruction memory, and then load instruction accesses the data memory. So using this address and load instruction access the data memory, then we can get data. Okay. So this is the result of the load instruction. And then, the load instruction is the I type instruction. So which means that we need to perform the x2 plus immediate. How? So if we see the list 5 I format instruction, so we can get the OP code field and the RD of the load instruction and RS1. So actually the load instruction has only one source register number, RS1, and then we can find the immediate field. Okay, so this is the inst 31 down to 20, right? So if we read the instruction pin number 31 down to pin number 20, then we can get 12-bit immediate number. And then I explained that this immediate number is the signed number. It's important. The signed number. Then how can you perform the RF underbar data, and then this data is indexed by RS1 plus immediate. So if we see that this equation, so this is the 32-bit data, the 31 down to 0, and then this is the 12-bit signed data. And then we need to perform add operator for the data from the register file plus immediate data. How?
아니,
Yeah, right. So we need the sign extension. So because the bit resolution is different for the operand and then this operand, then we need to set the bit resolution of the immediate field, immediate data to the 32-bit, like 31 down to 0. Okay. So that's why we require the immediate generator. So actually the input of the immediate generator is the immediate field from the instruction. Actually this immediate field is the different by instruction. So that's why this bit resolution is represented as the 32-bit, but actually for the load instruction, this immediate generator receives the 12-bit immediate number, like immediate 11 down to 0. Then immediate generator 32-bit number. And then which means that immediate generator performs extension. And then we require sign extension, right? Because the immediate number is the signed number. So what is the sign extension? Right. the MSB represents the signed bit of the signed number. So if we repeat the MSB, then we can extend the bit resolution of this output. Okay. So it looks like this: the immediate 11, immediate 11, and repeated 20 times, and then immediate 11 down to 0. So then we can get 32-bit signed number from the 12-bit immediate number, right? So using the immediate generator, then we can generate the 32-bit immediate number, and we need to perform the x2 plus immediate. So what is required? We need adder, right? And where is the adder? actually adder is included in ALU. Okay, so actually when I mentioned the R type instruction, the ALU received the RF data 1 and the read data 1 and then read data 2 from register 5, right? But when the load instruction is executed, the load instruction only requires read data 1 from the register file, and but we need to perform the add. So the another data is the extended immediate data, immediate 31.0. Okay, so when the load instruction is executed, then we need to change the input of the second input of the ALU using 32-bit extended immediate number. Okay, and then this ALU performs the add operation, then ALU generates the address. Okay, and then this address is given to the data memory. Data memory is the same. So it's the same to the instruction memory. So data memory is an array of the many entries. So the address is given, and we can read data from the data memory. But there are different kinds of memory instructions stored, right? So actually, we need to control the read and write of the data memory. Okay, that's why we require the memory write port and then memory read port. Okay, so when do we need the memory write control signal? So equal 1. When the store instruction is executed, then we need to store the data to the data memory, right? Then the mem write should be 1. And then when the load instruction is executed, then we need to set the mem read as 1, right? So these are the control signals.
Yeah, no.
That's very good question. And actually, in the register file, we have only one control signal called the read write. But in this case, we have two control signals, mem write and mem read. It's okay. So it's not a problem if we use only one control signal, like the mem write, because we can just distinguish load and load word and store word, load and store instruction. So that it's the same. It's the same to the register file. But we just use the mem read, just save the power consumption of the data memory. Okay, it means that actually the memory, these data memories are accessed by two instructions, so load word and then store word. Okay, but actually the address of this data memory is computed by ALU, right? ALU, and then actually the ALU is used for R-type instruction, arithmetic and logical instructions. So which means that this address input can be changed by also the other instruction. So which means that we can read some data from this data memory when this address is changing. Okay, so which means that this is also the kind of combinational logic. So which means the input is changing, the outputs are also changing. But it's hardware component, if there's some value of hardware is changed, then power is consumed, which means arithmetic and logical instructions are executed and this address values are changed, but you don't need this change, okay? Because the processor is executing arithmetic and logical instructions. So actually, we don't want to change the output of the data memory. If the output is changed, then data memory consumes power, so it's a waste of power. It's not good. Okay, it's related to the cost. So that's why we have the mem report. Okay, mem report is just required for saving power consumption. Okay. So this is the behavioral model of the memory. Okay. So this, as I mentioned, the memory is the data array indexed by an address. Okay. So which means that it's for the read operation, this is for load word, the load instruction. So read data becomes some value. So as you can see, this you can find the data array here, which means that data has the 256 elements, and then the read data is enabled when the mem read becomes 1, right? So which means if the mem read equal 1, the data is indexed by address. And then, also the size of the single element is the 32 bit. Okay, it's a 4 byte, which means that it's address divided by 4. Okay, address divided by 4. And if the mem read equal 0, the otherwise it is just 0. Okay, so output is not changing if the mem read is 0. Okay. And how about the mem write? So target, if the mem write becomes 1, the target becomes the data, right? So a certain element of data memory, and then this is also indexed by address divided by 4. And then I mentioned that we can just remove the RSC 2 bits to implement the divided by 4. Okay. And then this is updated by write data. Okay. So this is the behavioral model of the data memory. Then we need to also consider the branch instruction. The branch instruction is a little bit different because the branch instruction just changes the program counter, not register by and not data memory. So if we just see the BQ X1, X2, and then target. So what is required? So first, when a BQ is executed, then in order to execute the branch instruction, then we need to read 2 operand data from register file. So this is the RS1 and RS2. Then we need to perform compare operation because this BQ check the equality between 2 operands. How? It just performs the A minus B, right? If we not to compare the equality of 2 numbers, then we can perform subtraction, right? A minus B, and then check the 0. So if the A minus B becomes 0, then it means that A is equal to B. So which means that BEQ requires subtraction. So which means ALU has the subtraction operation. So read the operants data are read from the register file, and then these operands are given to the ALU, and then ALU check the 0. So ALU performs the subtraction, and then ALU check the 0 of the result. Okay, and then if the result becomes 0, then BQ update the program counter using target. Okay, and then if it is not 0, then the result of subtraction is not 0, then PC is the PC plus 4. Okay, that is the operation of the branch instruction. And how can you implement this operation? Okay, so the branch instruction also has this target field, and the target field is the immediate field. This is the 12-bit immediate number, right? But you know, the immediate field of the branch instruction is different from the immediate field of the I-type instruction. It is because the branch instruction includes the immediate 12 down to 1. Okay. Also, this MSB of the immediate field of the branch instruction is signed. So, which means also the branch instruction handles the immediate data. So we need to use the immediate generator. So using this immediate generator, this 12-bit immediate number is extended to the 32-bit signed number. Okay. And then, so actually the branch instruction the branch instruction, this immediate number is the multiplied by 2. So we need to perform the shift left by 1. And this immediate number is added with the current PC. Okay, then generate the branch target. So for the branch, so you can find that branch instruction requires another adder. So it is because actually branch. So in order to execute the BQ, then we need to perform subtraction, and then actually the subtraction is performed by ALU. So ALU is already occupied, which means that we cannot use the add operation of the ALU. That's why in order to support the branch instruction, a processor requires another add. And then this adder calculate the target of the branch instruction. Okay. So when the branch instruction, so this figure shows the full data path of the single cycle processor. So as I explained, the data paths are connected each other by some wires. I also explained about the instruction fetch stage, and then register file, and then also ALU, and then data memory, and then data memory, and then also this path is used for the branch instruction. Sometimes we require the multiplexer because, as I mentioned, the ALU can receive the output from the register file or immediate number. So which means that we need to select the input of the second input of the ALU from the output of this data 2, and then immediate number, which means that we require multiplexer. And then if we use multiplexer, then we require selection signal. Okay. And this selection signal is also a control signal. So the control signal should be determined by the instruction. So you can find the several control signals here. Also, you can find another mux here. It is because when the load instruction is executed, the RD, and then add RD. And then this RD comes from memory, and then this RD comes from the ALU. So which means that we need to, when the result is written back to the register file, we need to also select from the result from memory or result from ALU. So we also require the multiplexer here. And branch. So the program counter here, the program counter can be updated by the current PC plus 4 or target of the branch instruction. Okay, so which means we need to also select the source of the next PC from the PC plus 4 and target of the branch instruction. That's why we require the several multiplexers in our data path. The data path of the single cycle processor. So, okay, so so this time I briefly covers the data path of the data component, audio component of the basic data paths of the single cycle processor. And then by connecting this hardware component, then we can build the full data path of the single cycle processor. So when these hardware components are connected, then we also consider the pitch sources will be used for the some input of the next hardware component. So if there are two different possible sources, then we need the multiplexing. Okay. So I will stop here, and then I will also explain about the full data path of the single cycle processor in the next cycle and next class. And then I will also explain about the control unit of the single cycle processor. Thank you for your attention. Then I'll see you in the next class. Yeah, 감사합니다.